Hi everybody, welcome back. Hope you guys are doing good. Basically, we're about going to start in a few moments, but we still have 2.5 minutes. So for the time being, welcome back, and hope you're all doing well. Hey Ruby, good to see you. Hey guys. Hi Jamie, hi Valeria. Hey Rachel. Just about another minute to go. Okay. Hey Nathaniel. Okay, it's pretty much 11:30, so welcome back everybody. Hope you're all doing great. Today we're just going to have another of these meetings on logic, and we're going to do a few more practice problems to just give you a little bit more experience and ability to do the derivations. That's what the fourth homework is all about. So I want you guys to have as much capability and skill with this as you possibly can have. Hi, John Red. I remember last time I showed you guys how to do problem number 1 on the homework problem set, right? And I recall that some student asked, is there a way of doing this problem in fewer steps? And my response was that, well, basically not really, because it's going to take roughly about that number of steps to get to the solution. But when we solved it yesterday, or on Monday rather, there were 15 steps. And looking at the problem, there is another way to do it, which results in a couple fewer steps, just a few less, like 12. So I kind of wanted to show you guys an alternative proof procedure for problem 1. That doesn't give any further answers to the overall problem set, but it shows you how some of these problems can be solved in multiple different proof methods. So let's try this again. We're taking a look at the first problem in our homework problem set. And so problem 1, it says to derive that either C or not A. And you have these two assumptions provided at the beginning. First, that if A, then both B and not C. And then the second assumption that either C or not B. Okay, so, and hey there, Loveth and Marissa, good to see you guys. So last time what we did, if you guys remember, is we started by making the assumption of A for negation introduction. And then the whole proof went in a series of steps until we could get some kind of contradiction here that would allow us to then introduce a tilde to the letter A, And then once we have tilde A down there, we could simply disjoin C to its left. And that took 15 steps. But there's another method by which the proof could be done. Okay, so in this alternative version of doing the problem, let's begin with disjunction elimination. Okay, so I'm just giving you that as like a starting hint to get it started. So if that's the first step, then what shall I write as inference line number 3? What I'm telling you, let's do disjunction elimination. So how would the exact information be written on line 3? Who could tell me this? Go ahead, if you can. Let me know. What would be the information to input on line 3? Since I'm telling you that we're going to begin with disjunction elimination. What about that? Hey, Melanie, good to see you. So for my question, though, disjunction elimination, let it be the first rule that is used as we go forward in the proof. So in line 3, we're going to use that rule, but you must tell me, since I'm asking you, what would be the exact information that corresponds to using that rule on line 3. We're taking another look at the first problem on the homework assignment. These are the 2 premises, the 2 assumptions. We need to get to this result. Okay, so good, Jessica. You say assume, no, you're not even assuming A though, because if it's disjunction elimination, well, look at the disjunction. Where is the line that contains a disjunction in this problem so far? Tell me that. Which line has that? Actually, here's something I want to do. Sorry, we've been sticking with using a dual platform approach, and honestly, today it wasn't too important to me to have Zoom as our backup, because I don't necessarily need to do the screen share so much today. But I've noticed that the chat is a little bit more instantaneous, and because these proofs require a lot of quick questions and answers, I'm going to make sure that we get the full benefit of it. So hold on while I add the Zoom link to the chat. Sorry, just 1 second. It makes me do this dual authentication thing on my phone to get into the Zoom meetings. Okay, so meetings, logic practice problems. Here we go. Okay, so I'm dropping into the chat here the link for the Zoom. Go ahead, click that. As usual, this YouTube video will remain recording, and I'm just going to have the meeting here so that we can have a little bit more of a quicker chat, basically, and if there's ever a helpful reason for it, then I'll turn on the screen share. Okay, good, so here we go. We're all together. Just going to turn on the chat. Okay, so can someone just in the Zoom chat something for me? Yes? Hi, okay, good, Tanya, thanks for that. So, all right, you're saying that line 2 is where there's a disjunction. Okay, good. That's the disjunction, C or not B. So we are going to do disjunction elimination. Please tell me, what is the statement that we will write on line 3, since we're doing disjunction elimination? One suggestion was mentioned before that it should be assumed A, but that's not possible because A is not contained in the disjunction. So if you know how the disjunction elimination rule goes, please just tell me, what is the statement that I write on line 3, since I'm going to begin by doing disjunction elimination? Okay, good, Jessica and others. You're saying assume C for disjunction elimination. Correct. Disjunction elimination means that you assume the first disjunct of the disjunction on an available line, and then you're trying to show some result from that disjunct. Then you move on to part 2 of the procedure, which is that you then assume in a second subderivation the other disjunct, and you try to reach a common result from both. Okay, so let's now, on line 3, make the assumption of C for disjunction elimination. All right. Try to keep it a little small so that I can get it all in there. Okay, so what do you think I could do on line 4? Because now we've assumed C, so C exists on line 3. And if you look at what we are trying to derive, then maybe you have an insight as to what I could do on this line 4 to establish the result that I'm trying to derive. Who can tell me that? Line 4. As we continue the proof, we always go back and look at what we've been told to try and derive in the end. So you see the statement that we need to derive. You see what's available on line 1, 2, and 3. So then just tell me, what is a inference that can be used to add information on line 4 to take us right there to the statement that we need to derive? Go ahead and let me know what line 4 could be. Because the goal right now is to establish C or not A. Line 3 says C. So please, what do you think? There's 11 rules. So whatever this is going to be one of these 11 rules. Which one do you think it is that's going to allow us to add an information line on line 4? That's what I need you to tell me. I need you to tell me what inference can be done on line 4. Line 3 is a big hint. Line 3 contains the letter C. The statement that you're trying to derive in the end is that C or not A. So that right there should be enough for you to tell me what I can write on line 4. But you have to do it. So I mean, it could take all day, it could take 2 seconds. Just you have to type something in this chat and you have to tell me what is the inference that I'm going to make on line 4. Even if you give a wrong guess, you have to say something. Otherwise, we're just going to stand looking at each other. No, you would not reiterate 3 because it's already there. So there's no reason to reiterate it. Frida, you can't do conditional elimination. No, you can't do conditional elimination. Also, no, Jessica, because if you do conditional elimination, let's understand, how does conditional elimination work? With conditional elimination, you have a conditional, and then on another line, you have the antecedent of that conditional. Line 1 says A, then B, and not C. But you cannot eliminate line 1 because there's no letter A anywhere else in the proof. And Jessica, you say 2 and 3, conditional elimination? That's not possible because line 2 and 3, neither one is a conditional. If there's no conditional there, then you cannot eliminate something that doesn't exist. So it's not conditional elimination, no. Okay, so Jamie, you say do tilde B. Well, eventually we will, yes, Jamie, but not yet, because we can't move on to the second disjunct until we reach a result from C. And then after we get that result from C, we then infer from tilde B to the same result. So that's also not it, Jamie. But go ahead, keep trying. Think of the rules. Okay, Frida, you say, well, okay, so there's an issue here. Why are you saying negation introduction, but then you give a number? Because negation introduction doesn't work like that. You don't cite any number. You just say assume for negation introduction, and then you write also, I mean, I'm confused why you're writing tilde C. If it's a negation introduction, the result of that would be tilde tilde C. You would add another tilde to the existing statement. And there's no reason for us to want to have tilde tilde C. So not only are you not, giving the citation correctly, but it's also of questionable relevance why we would want to assume tilde C. What is the goal of the proof? What statement are we trying to reach? Tell me that. That's something that takes no real inference. What is the goal sentence? Just put that in our chat. C or not A, okay. Is there any way that we can write C or not A on line 4? Is there? Yes or no? If so, tell me how. C or not A is what we want to derive. Yes, we've established that. That's clear. But using the 3 inferences or lines that are here, how can we get to C or not A on line 4? Just you have to think of the rule. There's a rule that allows us to get to C or not A on line 4, but I'm not going to just tell it to you. You definitely have to think of it for yourself. So what do you think? C or not A on line 4, how's that going to be established? Okay, Frida, what's the line number that you would have to give? Yes, it's 3, okay? Disjunction introduction. What is disjunction introduction, everybody? Disjunction introduction allows you to add to the left or right of any statement that's already in the proof. Line 3 says C. What you need to derive is C disjunction, not A. So when you have the letter C, you need to think about what you have. You have C, and this is your goal. So you can simply just write C or not A on line 4 from disjunction introduction. On line 3. Disjunction introduction to line 3. Are we clear about disjunction introduction? Don't forget this rule, because I mean, I say to you, we need to get C or not A on line 4. I told you line 3 says C. I directed you back to this. You got to think about what I'm saying. You got to think, okay, well, he says C or not A is going to be what we write on line 4. How can I get to there from here? Well, if you have C already, and this is a disjunction, you know that you can create it by simply adding tilde A to the right of what's written on line 3. Okay, so did we get the result from the left disjunct? Yes. But that's disjunction elimination. We next have to do the same thing from the other disjunct. Okay? So then what is line 5? We're continuing with disjunction elimination. So what is the exact step to do next on line 5? Since it's disjunction elimination, there's a procedure for that. That's no guesswork. When you do disjunction elimination, what is the second part of it? What's the second part of doing disjunction elimination? Part 1 is you assume one disjunct, reach a result from it. How does part 2 then continue? Okay, good, Jessica. That's when you assume the other disjunct. Yes. So now we're assuming the right one. Now, even before we write more stuff, let me ask you, since we've now assumed tilde B, the right-hand disjunct, what is the goal of this new subderivation? To eventually take enough inferences until we get where? What's the goal that we're trying to get to in this little subderivation? If you don't know the goal, then you don't even know what you're doing. You're just sort of writing letters and stuff with no basis or no understanding. So what's the goal now that we've assumed tilde B? If you don't know what your goal is, then how can you possibly ever get there? What's the goal now? We've assumed tilde B. And we will eventually reach what? The way the disjunction elimination rule works. Okay, good. C or not A. Exactly. C or not A. We have to get the same thing from both disjuncts. So we got it once from the letter C. If we can do it again from the other side, then we've proven this statement, and that's when we're done. Okay, so we're now searching for C or not A inside of this subderivation. Okay, now let's consider how to get that. Who has a thought or an idea about what to provide on line 6? Because keep in mind, now our new goal, our little new sub-goal, is to get to C or not A. So what is a rule maybe that can be used to help us get to this C or not A result? Now we move on, and we're starting with line 6, searching for C or not A. So what can be written on the line 6? You know, look at the letters involved in the goal sentence. Look at the statements that are already in the proof. Understand these inference rules, and then consider what I can add on line 6. Line 6, what is that? No, you can't reiterate line 4 because it's in a closed subderivation. So we can't do that. Not going to be that easy. So let's take another attempt. This is a closed subderivation. This line breaks here. That's when it's locked away and it can't be used anymore. So we cannot reiterate line 4. But we still need to get to C or not A. So let's take a different route. What do you think? Okay, so Jamie, you say C or not A from disjunction introduction. But Jamie, what line were you thinking? What line were you thinking? You have to give a line number when you say disjunction introduction. So you're saying disjunction introduction on what line? You have to okay, when you do disjunction introduction, you have to give the number of the line that you're adding stuff to. But you can't do that because you're saying line 3, but 3 is in a closed subderivation. 3 and 4, you can't touch them. You can't reiterate them. You can't do anything involving them. You cannot state these two numbers. No. You have 1, 2, and 5. Those are the only available things from previous in the proof that you're still given access to. So it is not disjunction introduction on line 6. No. So we got to go with a different option. Let's try another thing. What do you think? Maybe if we cycle through all the rules, we'll get to the right rule. But you should be able to do it without just, exhausting all options. There's a certain option that's clear. So what do you think? Line 6. Hey, Jamie, I wanted to mention that you can't just write out disjunction introduction number free. You'd have to give a number. But if you look at the proof, you don't have access to any number that would result in C or not A. If you had 3, yes, you could do that. That's what we did on line 4, but now we've moved on to the second part of this disjunction elimination. So we don't have access to line 3 and 4. Nonetheless, we are looking for C or not A. So a different path forward. What do you think? Good. What do you think? Lots of rules that you're not even talking about. So let's try it. Let's try another option. You need C or not A. So tell me what to do. I don't know. I have no idea. It's up to you. Tell me what to do. Well, I'm just playing. Obviously, I do know what to do, but the important thing is that you learn, not that I just, repeat what I've already learned. So help me. Line 6. Some type of inference. Some type of inference that allows us to advance to the next step of the proof. You need to guess. You need to say something. Okay, so Dronrib, you're saying C, assume for disjunction elimination. Nope, already did that. That's over with. You see this? That happened already. We're done with that. We're on to tilde B. So no, you can't assume C again for disjunction elimination just once. So another option. Just keep going through the rules then. If that's the way you want to do it, just tell me. Okay, so Frida, you say A from conditional elimination? No, Frida. First of all, how is it that you say line 1? To do conditional elimination, how many different lines do you have to refer to? How many lines have to be mentioned anytime, every time that you do conditional elimination 2? So you can't say conditional elimination and then just list the number 1. You have to say 1, comma, something else. The something else has to be a line where there's just A, but we still don't have that yet. But Frida, if you're thinking you would like to be able to do conditional elimination, aha, that's a good thought. But for you to do it, you have to take it step by step. You're going to have to first get A in there, then you can eliminate the line 1 conditional, okay? So maybe now that's a little hint that takes us towards the answer. You want to do conditional elimination, so get the thing in the proof that will allow you to do it, and then you can do conditional elimination. So can we assume another letter? Yes, we can, Jessica, assume another letter. We can always assume a letter by using the negation rules. Okay, so what can be assumed on what rule? On line 6. Inside the second subderivation, we're going to do a sub-subderivation. Jessica, you say, can you assume another letter? I'm saying yes. So what do you want to do then? You should follow up. If you say, can you, so now propose which letter to assume. Frida and Jessica, your 2 comments, if I can mash them together, they're both like halfway correct at getting to the right next step. Okay, good. You say assume A. Jamie, you also say assume A, but you guys keep giving the wrong rule. Conditional elimination is not an assumption rule. Conditional elimination means that you have to have two lines. You don't make an assumption when you do conditional elimination. The assumption rules are conditional introduction, biconditional introduction, disjunction elimination, and negation introduction and elimination. Okay. It's not conditional introduction, no, because we don't want to establish a conditional. We just want to get the letter A. So, no, it's not assumed for conditional introduction, because look, if we assumed A here for conditional introduction, then whenever we close the proof, we're going to have A arrow something. And we don't need A arrow anything. We need a disjunction in the end. So we're not trying to build a conditional. So, I mean, you have to try again. It's like the last rule that you're going to tell me. Disjunction introduction doesn't revolve around making assumptions. It's not assumption when you do disjunction introduction. Disjunction introduction refers to an earlier line, which you then add information to. So you can't just say disjunction introduction and I'm writing whatever I want. You're adding to a previous line when you do disjunction introduction. So if you really wanted to use that rule, you would have to say a number, and then you would have to tell me what to write when I write out the full information on the line. So you can't just say, well, I see, Tanya, you say A for disjunction introduction. But when disjunction introduction is used, it results in a full disjunction, not just the letter A. So anyway, that's totally barking up the wrong tree. It is not disjunction introduction. No. It is not conditional introduction. No. But people are saying to assume A. So tell me a real rule that you can use to assume A. I mean, in this exact proof here. Okay, Lily, A for negation introduction. Very good. Negation introduction. You assume a statement, and then if you find a contradiction within the statement, after that, inside of the subderivation, it results in the opposite of that initial assumption. So let's assume A for the sake of negation introduction. Now, why are we doing this? Because if we find the contradiction, what will be the output of that subderivation? If we get a contradiction now within this subderivation structure, like say, for example, I don't know, B and tilde B somewhere in here, then what would be the thing that happens when we close that subderivation? When we close this subderivation, what is the output? The opposite, yes. So what is the opposite? Please say it specifically. It's tilde A. If we have tilde A then don't you see we'll be able to use disjunction introduction to simply disjoin C on its left, and then we will be done. Okay, so it's like this step right here is something that like you failed to see. You didn't think at all about negation, introduction, and elimination. So just don't forget that rule. That rule of negation, introduction, or elimination is oftentimes useful. So anyway, now we've assumed A. I hope that from this point, some of the remaining steps come into clearer focus for you. So what do you think is the option on line 7? This one is not the hardest. I mean, if you just look at every single line, go line by line, 1, 2, 3, 4, 5, 6. Look at all of those things and think of any rule that could be used to combine various elements of those different lines so that we can make a new inference. That's the thing about logic. It's not automatic. It's not something that just happens to you. I mean, you're the one who has to make the inference at each step. So if you're waiting for someone to come save the day or tell you what to do, it's only you. You're on your own with a lot of this stuff. So I'm here to help guide you through it, but you have to make the inferences because only by doing it will you learn it. Okay, so you say, Jessica, B and not A. Very good. Conditional elimination, 1, 6. Perfect. B and not A. Everyone hopefully are clear about this. B and not A, how did this get derived? Well, it is because on line 1, way back at the beginning, it says that if A, then B and not C. And on line 6, it shows A. Sorry, thank you, my bad. Thank you so much for my typo. Thanks, Jessica. B and not C. So anyway, back to what I was saying. Thank you. A is available on line 6. On line 1, it says if A, then B and not C. So those two combine to eliminate the conditional, and then we just get the consequent statement there. Okay, perfect. Now we have B and not C. Keep in mind that right now, at this point of the proof, we are within a subderivation, which is negation introduction. The negation introduction assumption means that we're basically looking right now for a contradiction. So look at the proof and tell me where this contradiction can be found. I basically have to have two letters or statements here that are opposites. So what can line 8 be? Based on what rule? Line 8. There's definitely some inferences that you have not used that apply to some of these statements here. So just help me add something on line 8. Looking for a contradiction. Where are two sentences or letters or whatever that are opposites on these numbered lines? Where can we see things that are the reverse of each other? Tell me, yeah, please, right now. What are two statements that are already in the proof that are opposite of each other? Okay, good, Samir. You see that there's B and there's also not B. So just come on, put them down there. Use rules to get them down there. Please, what's the next step? Samir, you said it, B and not B. Okay, come on. So if you see that it's B and not B, what rule can be used to just bring those down and put them at line 8 and line 9? Wait, Frida, huh? Tilde B and C, those are not opposites. A little confused. What are you saying? Tilde B and C are not opposite statements. B and tilde B are opposite statements. But what are you suggesting to do? Okay, so Jamie, let's reiterate line 5. Good. Which places tilde B right there? All right. Now we're at line 9. Samir, why are you leaving me hanging? You said B and not B and then just dipped out. I mean, that's when you should have said, okay, I know exactly what to do next. So if this is tilde B, next question, we need B. So where's that coming from? Yes, Jamie, it's from conjunction elimination of 7. This is a conjunction. It's an and sentence. When you have an and sentence, you can eliminate it. You can take one part off and provide it on another line. So B, conjunction elimination, line 7. Okay, so what are these two things? They are opposites. That's a contradiction. That's tilde B right next to B. So that means that now we close this subderivation because it started by assuming A for negation introduction. And how does these negation rules work? When you find the opposite pair, you basically close the subderivation, and what's the output? When the input assumption is A, you find a contradiction. What is the output that it spits out from the process when it's complete? That doesn't really require you to consider the logic of the problem. It's just asking you in general, when you have an introduction of negation, then what's the result at the end of that little subderivation? Yes, the opposite. So Frida, specifically, what is the information on line 10? It's tilde A. Okay, what's the justification over there? In the rule column, what would be that justification? Negation introduction 6 through 9. Good. Okay, now, here's tilde A. We're just 2 steps away, basically. So anyway, on line 11, what do you think I should do? Look up above at line 3 and 4, okay? And then look at line 10 and ask yourself, well, how can I write something on line 11 that's kind of very similar to what we did up here on line 3 and 4? Now I'm asking you to help me enter the information for line 11. And a big hint that I'm trying to give you is that it's much parallel to the step taken in line 3 to 4. Okay? So line 11. Yeah, go ahead, please. Line 11, it's a lot like line 3 to 4, that little step. So what do you think should be line 11 based on what rule? Line 3 and 4, that didn't help you at all? I mean, what is line 3 and line 4 inference move? Okay, look at that. Then come down here and look at line 10 and 11. Can you make that connection? What should be line 11? That's not enough help? Okay, so disjunction elimination. When you have disjunction elimination, you have to assume one disjunct, get to a result. Then you assume the other disjunct, and ultimately you're trying to get to what? When you do the second subderivation of disjunction elimination, what's the goal that you try to reach at the end of that? So I'm asking about the rule. Okay, Lily, and Frida, good. C or not A, disjunction introduction of line 10. I was surprised that my prompting didn't give you the answer, because if line 3 and 4 shows that we did disjunction introduction on 3 to produce this sentence, then you can tell that tilde A is just the right side of that disjunction. That's already now on line 10. So since we've found tilde A, we can disjoin C on its left. And that gives us C or not A from the, disjunction introduction of line 10. Okay, so then the last step is line 12. The other version of the proof that we did on Monday, there were 15 steps. It's just a little more work. This one we can do in 12. Since this is the last step, what is the information of line 12? Last line, last justification. What is written on line 12? And I mean, look, if I told you that it's the last line of the proof, then you already know exactly what the sentence is going to say. Because what does the last line of every proof say? It always ends with what kind of sentence? The sentence that you have been told to derive. So we should just say automatically, what is the written sentence on line 12? It is C or not A. C or not A, and the justification that you give is correct. Jamie, your justification is not correct, but Lily's is. It's disjunction elimination, line 2, where the disjunction occurs, and then you write the two sequences of numbered series where you have the two subderivations. So it's 3 through 4 and 5 through 11. And so that is another version of the proof of problem 1. Why would it be elimination, Jamie? Because it's disjunction elimination. This is assumed for disjunction elimination, and then we were able to get the result we wanted. But when you do disjunction elimination, you have to assume both sides of a disjunction. So we assumed C, and we got to the derived result. Then it's just a mechanical process. You assume then afterwards the other disjunct of line 2, and then you follow through inferences until you get to the same result. Same result, C or not A on line 4, C or not A on line 11. When you get the common result from the two disjuncts, that is when you close the second one and you write the common result outside the scope line of the second subderivation. That's just how the rule functions. So with disjunction elimination, you have to assume one side of it, find a result. Then second part 2, assume the right side, find the same result, however many steps it takes, you find that same result, and that is when you're done. In this case, the same result of both is the derived result we want. So that's why it's disjunction elimination. I mean, Jamie, there's no way for you to open a disjunction elimination assumption and not to finish it at the end. So we didn't even finish disjunction elimination until way down here on line 12. There'd be no way to continue a proof which opens disjunction elimination but does not close it. So now it's closed, and that's the end of the proof on line 12. Okay, good. So I'm just telling you that in the other version of the proof, we started instead by assuming A for negation introduction. And we did a whole bunch of steps until we finally got a contradiction that therefore spit out not A, and then we just disjoined C to its left as the final step. This is a slightly different procedure where we do disjunction elimination, starting with the assumption of C. And since C has been assumed, it's very easy to get this result because C is one of the two disjuncts. Assuming the other disjunct, it takes a little bit more work to get to the same result because notice tilde B is a different letter completely from either of these two disjuncts. So after having assumed it, your goal then becomes to find one of the two members of this disjunction. And knowing that line 1 is a conditional which starts with A, it would have occurred to you to assume the opposite of tilde A so you could eliminate that, and then you would have the material to build a contradiction. Okay, so that's just a second pass at the first homework problem of the homework problem set. And as I've said before, anybody who's working on the problems or needs a little bit of assistance or help is always fine to check in with me at the office hours or to even send me an email to make a different alternative time. Okay, so next I want to go through some more of our practice problems from the book. So here, just share the screen. And hopefully that's now visible. Okay, cool. So I'm looking right now at this part of the text. Let me just make a quick note to you about the way this looks. So 5.3, it's basically like a whole sequence of problems, A through R. We actually already did problem A a few weeks back, so I'm not going to do that one again. But when you see this little turnstile symbol, okay, so like you see here how in braces we have a sentence, and then over here there's this turnstile symbol, and then to the right another sentence. Well, what the turnstile means is that this is something that logically follows from the information on the left. So basically, you can interpret this as derive the thing that is on the right of the turnstile. Okay, so like this would be problem B. Derive that if A, then not B. And the premises that you're given, the assumptions, in other words, are just all the sentences that are grouped over here on the left in the braces, in the brackets. Okay, so let's try problem B, which is this one here. Okay, so this is problem section 5.3, part 1, problem B. Okay, so essentially you have to now derive that if A, then not B. And here's the assumption. The assumption is just that not B if and only if A. Okay, guys, so let's do this one. Let me begin with a hopefully not too bad of a question. What kind of sentence is this that you have to derive? What's the main connective and what is the name of that type of sentence? In this case, problem B, your goal sentence is no, it's not a biconditional, Tanya. The assumption is a biconditional. What you're told to derive is a regular conditional, just a single error there, okay? Makes sense, right? Okay, so you have to find a conditional. Now, what rule is usually used to build a conditional? It's right there in the name of the rule. It should be, I hope, kind of intuitive because even the wording of it makes it clear that this is building a conditional, right? So conditional introduction, yes. Conditional intro. How does the rule work? What assumption or inference shall we make on line 2 to get that started, to get that process of conditional introduction started? If you know that that's the goal, to get a conditional, then you think of the rule that introduces a conditional. And now you just have to take me through the mechanics of how it works. So what do I assume on line 2 in an effort to get to that conditional? Okay, Tanya, you do assume A, yes, but why have you written conjunction introduction? That's the wrong symbol. Okay, assume A for conditional introduction. Okay. Now, let's not be flying blind here. We've assumed A. What's our new goal? After having assumed A, we need to get to where? Within that subderivation, when will we close it? Once we get to what statement? Conditional introduction, how it works. You assume an antecedent of a desired conditional. And you continue through until, no, it's not B though, Frida. Look at the problem. It's tilde B, that's right. These little details matter though. It's the completely opposite. It's literally the opposite to say B from tilde B. So we now need to get to tilde B, right? Okay, so that's the goal here, but how will we get to it? What inference can you see on line 3 to get us where we're trying to go? Really, line 3? I mean, there's only 2 lines, so there's like really only one thing pretty much that you even can do at this point. What would that be? Okay, close, Frida, but you have to say the right numbering. If you're going to do biconditional elimination, how many numbers do you have to refer to in order to even say that rule? Correct, you have to give 2 numbers. So you have to give the number where the biconditional is, and then you also have to give the number where just the one side of it is. And so yes, it's 1 and 2. So that's tilde B, biconditional elimination 1 and 2. All right? So what about line 4? Maybe I don't even have to say much more. It'd be great if you could just tell me exactly what the last thing is here. Are you overthinking it? I mean, look at the problem and just tell me what's line 4. Okay, A arrow tilde B, conditional introduction 2 to 3. There you go, that's it. 4 steps, very easy. It's a conditional, so you have to do conditional introduction. There's no question, you have to do conditional introduction if what you need is a conditional. So you assume the left side, A. And then you continue making inferences until you find the right side, which is tilde B. We've assumed A, then you're supposed to look back. You're supposed to be like, okay, now that A has been added, let us look back at line 1 and see, does that change anything? Well, now that A is here, since this is a biconditional, I can use A to eliminate that biconditional and obtain the other side of it, which is tilde B. So A was assumed, and through inference, we reached the consequent tilde B. So we then close that subderivation once you get to the desired consequent. And then you write the full conditional where the assumption line is the antecedent, and the final line of the subderivation is the consequent. And then you just state the rule and the numbers that span over the subderivation for conditional introduction. Okay, so that's one of the problems. And let's see here. If you're looking at the whatever answer key, there you go. Couldn't be easier, right here. That's the same information that we see on the board. Okay, so let's move on to the next. All right, we're just going to keep drilling this. It's never going to stop. It's just going to be proofs on proofs. There's nothing left in this class except for derivations, derivations, derivations. So get used to it. Try and enjoy it. They're like little puzzles, guys. They're kind of like, I mean, they literally are logic puzzles. You're just trying to use inferences that you've learned, which are ancient rules, thousands of years old, and you're just using these rules to logically deduce statements from other statements. So we're going to keep working on it. So next is problem C. In the same section. So it's right there. What it says is derive L if and only if K. L double arrow K. And the premise that you have is a big conjunction. So the premise is just this. Both if K then L, and also if L then K. That's the assumption. Okay, so now we're starting. What's the goal sentence? What is the result, the type of sentence that we want to find as a result here? That's my question. It is a biconditional. Perfect, yes. So if it's a biconditional that you're trying to get to, what is a rule that allows you to build a biconditional? What's the name of that rule? Biconditional introduction, correct. So start going through the procedure of biconditional introduction right now. What's the first step to doing that? In this example where we're trying to build that particular sentence. You know that it's a biconditional you want. You know the biconditional intro is the rule to get there. Now you just have to use the rule. So let's use the rule and tell me exactly what to write on line 2 if I'm going to do biconditional introduction to get to this sentence. These rules, I mean, they're always the same. So the same way you always do biconditional introduction is the way that you would do it here. So just what's the way of doing it? Biconditional introduction, you need to know that. Biconditional introduction. I'm literally telling you what rule to do. Okay, so Jamie, no, you don't assume K then L, okay, because that's not how biconditional introduction works. So how does biconditional introduction work? A person assumes what part of a sentence in an order to get to what? Okay, so Jessica, you say assume L for biconditional introduction. Yes, when you have biconditional introduction, everybody, you assume one of the two sides of the desired biconditional, typically the left. So we assume the left side in an effort to eventually establish the right side. So L, assume for biconditional introduction. Now that we've assumed L, what is our goal internal to that part of the subderivation? By assuming L, we hope to get to where through a series of steps? The biconditional introduction rule. How exactly does it work? Jessica, I mean, you must know if you say to assume L. Well, what are the next steps of the procedure? A person assumes L. Well, yeah, so I see one question in the private chat. I'll get to that. Yeah, so Jessica, you're telling me K results from conditional elimination of 1 and 2, but no, I'm sorry, not quite. Because line 1 is a conjunction, and therefore you cannot do conditional elimination on it because it's not a conditional. It's a conjunction of 2 conditionals. So another little step has to be taken first before you are allowed to do conditional elimination, but you can after you take a certain step first. Okay, so Lily, conjunction elimination from line 1, that is what takes down L arrow K. See that? That's a conjunction sign. That means that this statement is conjoined to this statement. We can eliminate this conjunction and remove either the left or the right expression. So we've taken off the right side, which says L arrow K. And the reason we did that is exactly because we then want to use L to eliminate that conditional and just get to K. So, in the private chat, a student asked me, when would you assume, they asked, when would you assume the entire formula, like K arrow L? You would only assume a formula with more complexity than a single letter if that was what was written on the left or the right of the biconditional symbol in the sentence that you're told to derive. So, I mean, if this said A and B in parentheses, double arrow, C and D in another set of parentheses, then we could assume A and B, the whole formula, as parentheses. But in this case, the things that are on the left and the right, the things that flank the biconditional symbol on its two sides, they're just individual letters. And that is the reason that you would only assume the letter by itself rather than something more complex than that. Okay, but yes, so back, Jessica, and now I think you can track why we did this. We had to take this down first, so then we can do the elimination move. Okay, so I feel like you'll know then what to say next. Good, Jessica. K is our fourth inference line, and it's the result of conditional elimination on 2 and 3. Okay, so here's a question. By assuming L, were we able to get to the other side, K? Yes, that part is done. We got from the left side to the right side. But there's a part 2 to biconditional introduction. So knowing that, you're going to tell me now what is the next step on line 5. Because we're only halfway done with biconditional introduction. The way the rule works is you have to do from both sides. So good, Jessica, assume K, the other right-hand side. And that is for biconditional introduction. Okay, follow me now. What is the goal within this new subderivation? From L, we wanted to get to K. Okay, done, mission accomplished. Now we're assuming the other side, K, and where are we trying to get to from there? Like, I'm just asking the goal. Okay, good, Lily. It's to get back to the other side. Biconditional introduction works this way. You assume the left side of a desired biconditional, and through inference, you reach the right-hand side. Then you have a little break, and a second assumption is made, where you assume the opposite right-hand side and try and make inferences to get you back to the left side. So L leads to K, and if we can also show that K leads to L, then that is what it means for L to be related by biconditional to K. Okay, so here's K. The next few steps are pretty much very parallel to the steps above here. Okay, Frida, you say K arrow L, conjunction elimination of line 1. Very good, yes. Okay, so there's K arrow L. What about line 7 then? Maybe there's a reason why you removed K then L from line 1. I think there is, and you'll just tell me then what that allows us to do now for line 7. With each new additional line of the proof, new inferences become possible. Okay, so good, Frida. You say it's L, which is based on conditional elimination of 5 and 6, and that's right. All right, so just examine what's on the board. Has L led to K? Yes. And then in a second sequence, has K led to L? Also, yes. So when that has been accomplished, what's the final outcome of all that on line 8? Just how do we close and complete biconditional introduction? We show from the left, we get to the right. From the right, we get back to the left. That's when we complete the procedure and we write what on our line 8 now? We're at the end. You know, you can't give up when you get to the end. It's like you do all that work and then you're like, I don't know nothing else. No, come on. So L double arrow K, good. And that's biconditional introduction 2 through 4 and 5 through 7. Two through 4, 5 through 7. These two dash series are where we find the two parts of our biconditional introduction. 2 through 4 is the process of getting from L to K. 5 through 7 is the process of getting back from K to L again. And so biconditional introduction was used in both of those, resulting in the double arrow relation of L and K. So that's the answer for this third problem, problem C. And here, I'll pull it up so you can just see the way it's shown in the textbook. So here we go. Sorry, chat here, I guess. Yeah, so, oops. This is probably better then. right? So derive biconditional L, biconditional K, and you have a conjunction of these two conditionals. So we assume L, the left side. A couple of inferences later, we're at K. Okay, good. L that led to K. That shows that you're halfway done. We get from the left to the right of whatever the expression is. Part 2, assume the right and work way back to the left. So from L, we get to K through a couple of inferences. In a second step, we get from K back to L, as you see here. Then when that is done, we close the subderivation, and the result of it all is L biconditional if and only if K. And there are the citation of rules, as you see over there off to the right. Okay, so practice makes perfect, or at least practice makes better. So we're going to keep on doing more of these, and it's not going to stop. It will not stop. Okay, so D. As usual, do ask me any questions about anything that you're hearing or learning that isn't coming across clearly to you. It's always best to just deal with misunderstandings and confusion at the moment rather than letting them pile up and then finding yourself lost or confused later because you didn't ask questions earlier. So I always want you to make sure you're feeling okay to do that. Here's problem D. Okay, so what it says is you need to derive not M. Okay, and what we have are two sentences for assumptions. So the first one says that M if and only if T. And then the second one just says not T. All right. So there we go. Now we have to find a way to prove not M based on those. So what kind of sentence is it that we are trying to derive? That's my first question, as usual. What kind of sentence are we ultimately looking to find as a result of problem D? It's called a what? What kind of sentence is that? It says derive. Well, Jessica, 1 second though. I'm asking first of all what kind of sentence it is. Negation intro is a type of rule, but very close. The sentence is just individually called. It's a negation, okay? So this is a negation. It is a negative statement. It's the denial of M. So when you want a negation, one rule that you should think of is a rule which has that word in its name. And Jessica, what is it called again? Or anybody else? To build a negation, we should definitely consider the rule otherwise known as what? Negation intro, good, okay, just now we're clear. We are now going to try and do negation introduction to find tilde M. So if we're going to use negation introduction as a method to get tilde M, what will we assume on line 3? Okay, you got to just tell me that. We want not M, you're saying use negation intro, all the parts, all the pieces are there. You now just put it together. Okay, good, so assume M for negation introduction. Okay, great. Now we have M. We have assumed it for negation introduction. Why? Well, because we want to get to its opposite. By assuming this and finding a contradiction, the output of that will be the goal, and we will then be done. But we'll take our steps. So now we have M. Look above, and with the addition of M on line 3, ask yourself, and please tell me, what inference may now be done involving these sentences that are all available on lines 1, 2, and 3. You have to sometimes, look at letters that appear in multiple of the different sentences and then consider what rule allows you to apply any inference to them. So, Kalia, you say T is the result of biconditional elimination of 1 and 3. Yes, good, the biconditional simple. So there we go, T, biconditional elimination 1, 3. Okay, so there's T on line 4. Maybe I don't have to say much. I love it if it starts getting a little bit more you doing the lifting and stuff on these works, on these problems. So great, reiterate line 2 and bring tilde T down into the subderivation. Okay, so that's the reiteration of 2, which means that what? Now we've gotten to what point? on line 6. Line 6. Good, yes, exactly. It's the result. It's tilde m. And how did we get to it? Well, it is because of a contradiction here. So in other words, it is negation introduction spanning from line 3 down to 5. So there's a simple proof of tilde m based on these two premises or assumptions. Let's see, pull that up, and then you'll just be able to see it. Yeah, so here we go. Display it here in the chat, or sorry, in the screen share. We need to get tilde m. We have a biconditional and negation of t. So we just begin by assuming m to eventually close the subderivation and get the reverse. Once m has been assumed, though, as you know, we can eliminate that biconditional using it, and that releases t. And then tilde t is already here above, and that can simply be reiterated, and that gives us the opposite contradictory pair. So the closed subderivation then results in tilde m on line 6. So that's yet another one of these problems. I mean, again, just as a reminder about how negation rules work, if you assume something to be the case, but it implies something contradictory, then that assumption cannot hold, and the opposite must be true. So, like, let's assume that that I'm not alive right now. Okay, like suppose the statement "Dr. Vulich is alive" is false. So if I'm alive is false, that means that I can't be giving a lecture, but I am giving a lecture. So clearly, the statement that I'm not alive is not the case, and in other words, I am alive. So like from any assumption of something, if it implies two impossible things, like two things that cannot both be true, then that means we can eliminate that assumption, and the opposite of it must be the case. You know, so like the Earth, it's not flat. Suppose that it was flat, though. Assume F for Earth is flat. Well, that implies that objects will just fall off the edge of the Earth because there's an edge. But we know that that does not happen. And so because this contradiction seems to be provided for by the assumption that Earth is not flat, we can thus safely conclude, that the Earth is not round, that it is in fact round. So any assumption which leads us towards an opposite absurd contradiction must be rejected, and the opposite of it is true. I'm not sure if I perfectly well said that, but let me try one more time. The Earth is round, so the statement that it's flat is false. Assume for the sake of discussion that it is not round. Or in other words, assume that the statement that it's not round, meaning that it is flat. If we assume that, then we are now going to be drawn towards absurdities, logical contradictions. So we thus must reject that assumption, which we made for the sake of argument, and conclude with its opposite. Okay. So I'm going to try another one really quick. We still have a bit of time, and the more practice that we get, the better it is for all of us. So let's look at the letter E, which is the next one up. Okay. Yeah, I think what I was trying to say is, so the statement that it's not flat is true. Assume that it is flat, which is the reverse of that it's not. And if it is flat was assumed, that would lead towards these things that are, contradictory. So that allows us to assume or conclude that it is not flat. Okay, letter E. So we just have to derive C. And this one's actually, I think, pretty easy, but maybe it'll take a moment of thought. All you have is this, B and not B. So what'll I do? How can I get C? Okay, so Jessica, you say, oh wait, that's from before. Yeah, but let me refer to your question there, Jessica. To get to tilde M in the previous problem, we needed to get a contradiction. Yes, a pair of opposite letters, but it sometimes is the case that the opposite pair is not just a single letter, but a whole formula. So say you have A and B, and then below that somewhere you have parenthesis, tilde outside the parenthesis, and inside it says A and B. that can also be an opposite contradictory pair. So all there has to be is a tilde attached to either a letter or a whole formula, and then the unnegated version of it somewhere else. So either an individual letter or a formula, but they just have to be opposites because of the presence of a tilde on one that is not present on the other. Okay, so, but yeah, here we have C as the goal. And oops, I'm sorry, guys. I don't know why I did that. Apologies. We can both see here in the screen share that I meant to write B and not B. So yeah, we have B and not B. Good, thank you. I'm sorry, Frida. Thanks for the correction. I noticed it just now too. So yeah, B and not B is our one assumption, and we have to derive C. So what do you think? What should be done to get to this letter C? This one, I mean, is, I don't know if it takes a moment of thought, but once you understand what it is, it's actually one of the easiest problems. Very few steps. We need to get C. And all we have been told is that both B and also not B. So this whole discussion of negation, introduction, and elimination should help you now to come up with the right answer for me. Okay, well, Frida, you say B from conjunction elimination on 1. Good, yes. Ultimately, we will have to take these two letters out and remove them from the conjunction, but we're going to have to do it within the scope of another assumption that we have to make first. So that's a hint for us. I'm not saying you're saying something wrong, Frida, but it just has to be done a little bit later. Okay, so Jessica, you're giving the wrong rule, Jessica, and you're also giving the wrong thing to assume. So when one says conjunction introduction, that's not an assumption rule. Conjunction introduction relies on already having 2 lines where you put them together with a conjunction sign in between the 2 lines. So conjunction introduction doesn't even involve an assumption. Also, if what you're thinking of is doing the negation thing, you have to assume the opposite of what you want. So you would not assume C, because C is what is to be proven. You would assume the reverse of C, and then by negation elimination, show the contradiction. So Lily, you have the right idea. Let's assume tilde C, and that is for negation elimination. Okay, because we want to eliminate this tilde so that just regular C is the byproduct at the end. So since we're now doing negation elimination, yeah, so good. How does a negation rule always work? Whether it's elimination or introduction, the basic same procedure exists. You have to find a what? To close the negation subderivation. You have to find a contradiction. Correct, Frida. So do you see a contradiction here that we can make available for use? If so, please help me to put the 2 parts into this subderivation. What rule can allow me to put those things where they need to be so that I can finish the proof? The parts are all there. Okay, good, Frida. So you say B is conjunction elimination of line 1. Yes, it is. But we're only halfway there because we also need to have the opposite of this. And if you're looking at the proof, you should see how to do that. So what is the next step you think? Okay, good, Frida, is tilde B. And that's also conjunction elimination of 1. So what are these 2 things? Well, they're opposites. And so according to the rule of negation elimination, once you do have the opposite pairs, the contradiction, the next step after that is to immediately just do what? You then close the subderivation, and you write at the bottom, below the subderivation, the reverse of the initial assumption. So in this case, it's C, and that's on the basis of, do you have it there? Negation elimination 2 through 4. Okay, so that's another little practice problem and another proof for us. And here I'll show on the board, or sorry, in the chat, the same problem here. 5 little steps, and there they are. Assuming tilde C for the purposes of negation elimination, and knowing that on line 1 there's a, and that releases C from the subderivation. You know, to be honest, this problem, it could have told us to derive anything. What if it said derive parentheses A and K. If that had been the case, then what would have been your assumption on line 2? If it said derive A and K, then in that case, on line 2, you would have initiated the proof by assuming what? I'm just saying hypothetically, suppose it was this problem. Then if this was the goal, what would have been your initial assumption here? Good, Lily. It would have been the assumption of tilde A and K. And that would have been assumed for what? Negation. Who knows the name of the rule that I would have written here in case this had been the problem? Negation elimination, right. So to an earlier private question in the chat, a student said, well, when are you going to assume more than just a letter? It does depends on the purposes or the needs of the proof. In this case, because we need this whole formula, we assume the, opposite of the whole thing, braced within parentheses. Negation elimination will output the unnegated version of this sentence, which is what we want here, and the same steps would follow afterwards. You'd have B and tilde B from 2 steps of conjunction elimination on 1, and then on line 5, that would result in A and K for negation elimination 2 through 4. So all I'm trying to mention is that if you have a contradiction like so, like a conjunction of 2 statements that are opposites, or if you have a contradiction anywhere in the available lines that you can use, then those 2 opposite things, together with the use of a negation rule, will allow you to establish anything at all. So I see a question here in the chat, but it's on private, so I'll just read it to everybody. If the connective is not present in the assumptions, you always have to assume it. Well, no, not necessarily, because sometimes there's no need for an assumption. Say, for example, you had this as a problem. It says derive A and B. This is a very elementary problem here that I'm going to show, but suppose that this was what you were working with. Can you tell me what I would do to add information on line 3? How do I get to the result I want now? To the one who's asked me the question or anybody else, this should be very easy. I mean, come on, I need to prove A and B. Okay, so yeah, A and B, conjunction introduction of 1 and 2. Now, the question that was stated in the private chat here says, suppose the connective is not present in the assumptions, do you then have to assume it? Not necessarily. In this case, there's no connective in either of the 2 assumptions. But notice that we haven't made any assumption to get to line 3. We just combined those 2 things using this rule. So it just sort of depends on the case. In many cases, yes, you will have to make an assumption that brings a new connective into the proof. But in other cases, that connective can be generated without assumptions by means of doing inferences instead of assumption rules. Okay, so good. All right then, guys, so that's about it for today. That's all we had time for now. But, you know, we're going to have plenty of more time to work on the problems between now and when they're due. And I'm always happy to help out by office hour or by email or anything else. So let me know, be in touch. For now, though, I guess have a great day. I'm going to close both of our chats in 2 steps. So first, I'm ending the Zoom meeting. Thanks again, everyone, for all of your hard work and attendance. And I'll see you after the break. I know we have, I guess, our long holiday break coming, so enjoy Thanksgiving. I don't know if you're going to see family or if you're going to kind of keep it chill. Probably a lot of people are worried about the possibilities of the virus. So whatever you are going to do, I really wish you well. I hope you have a good, restful holiday. But yeah, I'll be in touch. So see you guys soon. Thanks. And then one more quick closing of this not subderivation, but meeting. Thanks again, guys. I'll see you then next time. Okay, bye.